Okay, so on Monday's lecture, we first completed our discussions of magnetic systems. We looked at the quantum mechanical treatment of magnetic dipole. But more importantly, we started the discussion of the grand canonical ensemble. The main problem we were addressing here is we have a system which interacts with the environment, and it exchanges both energy with the environment and also a number of particles with the environment. The number is not fixed. And now we said that the probability that the system will be in some microstate, let me denote by R, now this R also represents the number of particles also in my system, was given by e to the power minus beta E minus mu n over the grand partition function. So again, I repeat, this is the probability that my system will be in one particular microstate. And this grand canonical partition function was given by the sum over all microstates. Now this time the microstates can also have a different number of particles, number is also variable, of this exponential factor. And then we also discussed that, since we know the probabilities, we can calculate the average energy, which will be given by the derivative of the logarithm of this q with respect to beta, with a minus sign, keeping mu and v constant, and the number of particles can be written as derivative with respect to mu of logarithm of q, keeping t and v constant, times kt. Or we also defined another parameter which we call the fugacity as e to the power beta mu. In terms of this parameter, q was written as the number of sum over again the microstates of z to the power n e to the power minus beta mu. So again, in terms of this definition of q, in terms of the fugacity and the temperature, so this is not mu, this is E. The average energy can be written as derivative with respect to beta of logarithm q, but this time keeping z constant. Sorry, here this is wrong, this is not correct. That is not correct because if you take the derivative with respect to beta, you get epsilon minus mu n in front of the exponent. So this is the correct definition of the energy. It's the derivative with respect to beta, but keeping the z constant. Remember, z depends on both beta and mu, but we are keeping z constant while changing beta, essentially telling me that I'm also changing mu such that beta mu is constant, even though I'm changing beta. And the number of particles would be just z times the derivative with respect to z of logarithm of q. Now we said that in particular, if we have a system of non-interacting particles, we looked at the ideal gas. For non-interacting particles, you see this grand partition function can be written as sum over n, all number of particles is possible, sum over the microstates of n particles of z to the n e to the power minus beta E. Now, since in the second sum n is constant, I can take it out, but if I take that out, this becomes sum over n z to the n. This is the canonical partition function for n particles. This is again quite general. This is valid for any system, in fact. But if we have non-interacting particles, we know that Qn can be written as the partition function for one particle raised to the power n divided by n factorial. These are just particles that are not interacting, but they are free to move around so that they can exchange. And hence we have this Gibbs correction factor we divide by n factorial. Yes?
In the presence of the chemical potential, can we say line term? Can we talk about nothing?
Sure. You see, chemical potential is a macroscopic property. It doesn't influence the microscopic property of the system.
I think it is negative, right? All the time.
No. For bosons, negative. For fermions, it can be negative or positive. We will see. We will study that. Now, if this is the case, then Q just becomes sum over n z times Q1 raised to the power n divided by n factorial. Number of particles can go from 0 up to infinity, but this is nothing but the expansion of the exponential. This is for non-interacting free particles. Well, up to this point, we are not making any assumption about their internal structure. They can be point-like objects, they can have an internal structure. We will see what that internal structure will change when we will study that problem. But for the time being, if there are just, it can be complex molecules, if the molecules are not interacting with each other, they are free, there is no external potential here. So this is the partition function. The grand canonical partition function expressed in terms of the partition function of a single particle. Now we also looked at the oscillator problem. The difference between the previous case and the oscillators is now there is an external potential, so that these particles are fixed close to a point. So we don't have exchange of these particles. So then we don't have this n factorial. In this case, Qn is just Q1 to the n, and the grand partition function just becomes sum over n z times Q1 to the n which is 1 over 1 minus z times Q1. So any questions up to here? Okay, if we know the grand canonical partition function, the number of particles, I'm not putting the average sign, but since in the grand canonical ensemble the number is constantly changing, what I mean is the average number of particles, and is the derivative with respect to z of the logarithm of q. So for the non-interacting free particles, logarithm of q is z times derivative with respect to z of z times q1, which is just z times q1. Now, in particular, if you think what q1 is, q1 would be d cubed p, d cubed q, divided by h cubed, e to power minus beta e, as a function of p. Basically, the energy of my system will depend on p plus the internal degrees of freedom, if there is any. But the important thing is q1 is proportional to the volume. So this will be, the number of particles will be z, whatever the fugacity of my system is, times the volume. What remains is just a function of temperature. This is for a non-interacting gas. Now for oscillators, n will be again z times the derivative with respect to z of the logarithm of qn, which will be minus the logarithm of 1 minus z q1, which will be z times, if you take the derivative of this logarithm, you would get q1 divided by 1 minus zq1, or zq1 divided by 1 minus zq1. This is n. And you can solve for this. This will tell us that z of q1 will be actually 1 minus 1 over n approximately, plus corrections of the order of 1 over n squared. Remember, n is a huge number, a number with 23 or more digits. So 1 over n is just zeros after the decimal point, 23 zeros and some number over there. So this is, okay, 1 less than 1. That is nice because if it wasn't less than 1, we couldn't carry out this summation over here. But it is almost 1. Secondly, Q1, since they are oscillators, they don't really feel the volume. And Q1, in this case, depends only on the temperature. You see, Q1 would be d cubed p, d cubed q, divided by h cubed, exponent minus beta, p squared over 2m plus 1 over 2m omega squared q squared. You can basically integrate both omega and q. There is no volume appearing over here. So this is just some other function of gt. So here we have z times q1, z times g of t is basically just 1, effectively 1. It's exactly 1 if we take the limit n goes to infinity. For finite n, it is very close to 1. So which tells me that z is equal to 1 over gt. Now these particles vibrating around their equilibrium point is nothing but a model for a solid. So if you consider a solid, you have all these atoms, their positions are fixed, but they are allowed to vibrate close to their equilibrium point. And for these solids, the fugacity of the system is some function of temperature only. What is that function? Well, it depends on your material, the properties of your solid, etc. But the crucial thing is it only depends on the temperature. Now let's look at solid-gas phase transitions. Basically, this is what happens when you get sublimation. Now, the basic ideas that we will discuss here will also apply to liquid-gas, liquid-solid phase transitions, but at least for solid-gas phase transitions, we have more rigorous results. So let's imagine we have a system. There is solid. Let me show it like this. This is the solid phase. This is the gas phase. Well, if you consider it, the solid phase and the gas phase, they can exchange energy. They even exchange number of particles. The solid can evaporate and the gas can solidify. So they are exchanging particles, they are exchanging energy. And we had already seen the equilibrium condition for such two systems. In equilibrium, since they exchange energy, their temperatures have to be equal. This is an equilibrium condition we have. Furthermore, since they are exchanging particles, their chemical potentials have to be equal. But if you combine these things, remember, the fugacity is e to power beta mu. Beta is the inverse temperature. Both phases have the same beta and the same mu. Basically, the fugacity of the gas phase has to be equal to the fugacity of the solid phase when we have this liquid-gas transition. Well, what about the fugacity of the solid phase? We don't know what it is, but we know that it is some function of temperature only. This is for the solid phase. So for the solid, we have 1 over some function of temperature. Now for the gas phase, well, we can solve this expression for Z. It is n over V times some function of temperature. This is the number of particles in the gas phase divided by the volume of the gas. Now, in particular, the number of gas particles divided by the volume of the gas is some function of temperature only. Now, we don't know what this function is, but we know that it's a function of temperature only. It doesn't depend on the volume. So what does it mean it doesn't depend on the volume? Well, if V increases, this tells me that N is also increasing. If V is decreasing, if you try to compress this gas, the number of gas particles will decrease. You will solidify. The gas will solidify. If you increase the volume, the solid will evaporate. If you decrease the volume, if you compress it, well, the gas will solidify. So that the ratio will be constant as long as you don't change the temperature. Now, furthermore, remember, the gas satisfies this equation, PV is equal to NKT. So P is equal to N over V, well, let me put the gas, times KT. If we have a gas in equilibrium with its solid phase, then this equation should satisfy. So the pressure of the gas will be given by Boltzmann constant times T times F of T divided by G of T. Well, the right-hand side only depends on the temperature. It doesn't depend on the volume. So what will happen? Let's look at how the pressure of the system as a whole changes as a function of volume. Suppose that we have our gas at a very large volume. It's an ideal gas. It will satisfy the ideal gas law. So PV will be equal to NKT. At a fixed temperature, the pressure will be inversely proportional to volume. This is the pure gas phase. Well, let's look at this expression in a slightly from a different perspective. The total number of my system is actually larger than the gas molecules, well, some of them solid. The number of gas molecules is the volume of the gas times F of T over G of T, some function of temperature. Well, we can even write this as V times F of T divided by G of T. Essentially, solids occupy a very small volume compared to gases. So the total number of particles have to be larger than V times that function of temperature, whatever that function of temperature is. But at a given temperature, if I'm lowering V, eventually F of T over v times f of t over g of t will be equal to n, so this condition will no longer be satisfied. Well, what that tells me is that not all molecules can be in the gas phase anymore. As I'm lowering V, some of the particles have to go to the solid phase. So now we have both the gas and the solid at the same environment. So we get this solid gas equilibrium. But if there is a solid gas equilibrium, pressure doesn't change. If you change the volume, pressure is now just a function of temperature. So if you compress the system further, the pressure remains the same, mainly because if you reduce the volume, more gas becomes solid, so you have less gas molecules, and hence the decrease in the volume is compensated by the decrease in the number of gas molecules, and hence the pressure will be constant. This is a mixture of gas and solid. But eventually, everything becomes solid. If you keep compressing the system, everything becomes solid. So if you try compressing solids, well, the pressure has to increase very fast. This will be what you will observe. This is our phase transition curve. Where does this transition start? Well, it depends. You see, this is the equation that governs the onset. When v times f of t over g of t is equal to n, that is when we start to have solidification or phase transition in general. So if you change the temperature, the volume at which this happens might be different. So for example, at a higher temperature, you might end up having such a diagram. At an even higher temperature, you might have such a diagram. At a different temperature, you might have this diagram. It depends on your system. But for example, if you have such a diagram, what you see here is there is this region where there is a phase transition, where you get a mixture of gas plus solid. Different phases mixed there. You get a mixtures. Here you have pure phase. In this case, it's a gas. On the other side, you can have another pure phase. That's a solid. But you see that above this temperature, you don't have a phase transition. Phase transition basically disappears. This, for example, happens in the phase transition between liquid and gas. Because how do you distinguish a liquid phase from the gas phase? How do you distinguish liquid water from gas water? Yes? How do you distinguish them? When you see water vapor and water, can you distinguish them? I hope you can. What is the distinguishing property? Density, or the volume per molecule, volume per gram. Gas has a much larger volume than solid, for example. The relative separation between the particles are larger in the gas phase than in the liquid phase. But what happens if you compress the gas? Well, it will try to liquefy, but if you increase the temperature, it cannot liquefy. So you get a very dense vapor. Then you can say, okay, the liquid water molecules interact more strongly than in their gas phase. That can be another argument you can have. But if you are at a very high temperature, the kinetic energy, the thermal energy of the molecules is much, much higher than their interaction energy. So basically you can ignore that. So if you are at a sufficiently high temperature, well, and sufficiently high pressure, let's say, you cannot really distinguish a liquid from a vapor. There's no phase transition, basically disappears there. That's called the critical point.
Can you give an example of this?
Water vapor and water, liquid water. That's an example.
Can I experience such situation naturally?
What do you mean natural?
Like inside a cloud or something, or mountain.
Natural on Earth, you mean?
Yeah.
Let me see. Do we have such a? No example comes to my mind at the moment. But we know that water has this property. Of course, to see that you have to go to higher temperatures, higher pressures, etc., which you cannot create in your everyday life. You see, in everyday life, the parameters we have lie within a very limited range.
Can we give some number for example?
I don't remember the numbers. Your book has the numbers. Look at Patria there, he quotes the numbers. I don't remember them. What about the PT diagram? How will it look like? Well, let's see. At a high pressure, at a small pressure, high temperature, we expect everything to be gas. So here, somewhere over here, we have gases. Let's say that we keep the pressure constant, but reduce the temperature. If you consider the ideal gas, if you are reducing the temperature, keeping the pressure constant, you are also compressing it at the same time. Well, if you compress it well enough, eventually it will solidify at some point. This is one possibility. Another possibility, it will first liquefy and then solidify. At an even higher pressure, let's say, you see, there will be this line. Now let me draw it like this. There will be such a line in the PT space, which will separate the gas and the solid phases. That will happen at a sufficiently low pressure. For example, if you take ice to space, that's a very low pressure environment, you won't observe the liquid phase. It will just evaporate. from solid to liquid. Or if you had ever experience with dry ice, that's just frozen carbon dioxide. That just from the solid phase, it evaporates into the gas phase. At a high enough pressure, there will be the usual transition that we see in water. Solid, gas, liquid, solid, liquid, gas. But then, as I had mentioned over here, it might happen that some of these lines separating different phases end. They just end there. There's no phase transition above that. So this is called a critical point. This is called the tricritical point. For example, for water, the tricritical point should be around 0.01. You see, at the tricritical point, you have both the liquid, gas, and the solid at the same time. How we can do that? Well, just pick up a container, take a container, isolate it, and freeze it. So it will be at a very low temperature. Now, it's all solid. Now, as you keep heating, it will take heat from the environment. Some of that will melt. There will be a gas phase appearing. And at the temperature when both the gas phase and the liquid phase appear, that is the point of tricritical point. So that's a fixed temperature. So if you create this system, you can use it to calibrate your thermometers. It's not really at 0 degrees Celsius because the pressure is lower than the atmospheric pressure. 0 degrees Celsius is the freezing point of water at atmospheric pressure. Since at this tricritical point, the pressure is lower than the atmospheric pressure, it freezes at a slightly higher, different temperature. So any questions about these phase diagrams? And by the way, you see, this point, if I pick up a point over here and a point over here, point A and point B, well, it's hard to say whether they are in the same phase or a different phase. So you can separate two phases if there is a very radical change in some property of the system. For example, what can change is the volume suddenly increases. There is a sudden change in some physical property of the system. Now, but if I look at these A and B systems, okay, I can go from A to B along that line. Then I would say, oh, there's a phase transition, definitely. So these two are different phases of the same system. But I can also go along such a path. And then it will be just a continuous change in my system. It's like compressing my system at some temperature, etc., some varying temperatures. There's no phase transition along that second curve. So this concept of phase becomes a bit vague, especially if you have such a critical points in your system where the phase boundary between two different phases just terminates. It still makes sense for states in the near vicinity of this phase boundary. So they will have very almost identical. Some of the properties will be identical. They will be almost at the same temperature, let's say. But they will have radically different other properties. So it's easy to compare them. But if you have two states like A and B that are very different in terms of temperature, pressure, etc., well, saying that one is a liquid, one is a gas won't be so trivial. Stating that they are different phases won't be so trivial. Or if, for example, in the case of liquid and solid transitions or gas and solid transitions, usually you don't get these critical points. Well, that also depends on what you mean by a solid. And solids in the sense of a crystalline solids, you don't get this critical point. The phase, there's always a phase boundary separating different phases, mainly because if you consider the crystals, they have certain symmetries. Symmetries cannot continuously change from existing to non-existing. They either exist or do not exist. So that makes a sharp distinction between a solid and a liquid, or a solid and a gas. But such a sharp criteria doesn't exist between liquid and gas.
We cannot distinguish liquid and gas phases for such systems by thermodynamically, or
Never,
we can
actually.
detect at all?
I mean,
Any system needs.
well, there is no, let's say that I take one system that's at a given temperature, at a, let's say, a high temperature, a high pressure, somewhat a high pressure. Another system that's also at a high temperature, at a high pressure. How can I tell whether one is a gas or one is a liquid? I need to compare them. So one way of looking at it is, how can I change one to the other one? If I can continuously change if I can change one to the other one, during this change, if there is a phase transition, and phase transition is quite a radical event. Things diverge, in fact, during phase transitions. If there's such a radical change, then I guess, oh, definitely these two are at different phases of the given material. But I cannot do that if these two systems are really separated in this PT plane, let's say, because now I have other ways of changing one system to the other one without going through phase transition. I can continuously change one to the other one without any discontinuity. Then, well, how can I say that there's a phase transition? You see, I have gases at different densities. I have liquids at different densities. I'm just saying that, oh, the density should be high or low won't be a general criteria for saying that one is a liquid, one is a gas. So that's what I'm saying. But of course, if they are very close to this phase transition line, then of course you can say that, oh, they are different phases, like these 2 points. But still, I mean, where's the boundary? In which region you can distinguish a liquid and a solid, in which region you cannot distinguish a liquid and a solid. Now let's look at how the pressure changes during this phase transition. What I would like to do, well, we know that the pressure let's look at this one. How does the pressure change? Well, I draw these lines.
Can you explain a bit more you are talking about symmetry?
Yes.
Can you explain a bit more? For example, for every phase transition, we should observe some kind of a symmetry breaking?
Well, not necessarily. So which kind of symmetry breaking are you talking about?
This question because in literature, as far as I know, for example, electroweak symmetry breaking is also called as phase transition. So we expect such a symmetry breaking, some symmetry.
Yeah. Let me ask you this question. Does the gas have a larger symmetry than the solid?
I was going to ask that in this case, we are we talking about degrees of freedom in terms of symmetry, what kind of symmetry are we talking about?
For example, let's look at the sodium chloride crystal. It has a cubic crystal structure. Yeah, this kind of symmetry I'm talking about. But I mean, any kind of symmetry, let me say. That it's easy to visualize the symmetries in space, in visual symmetries. So this is, one will be, let's say, sodium, the next one will be chlorine, sodium, etc.
I guess solids are more symmetric than liquids, and liquids are more symmetric than...
Well, let's see, what is the symmetry of the sodium chloride, assuming that it's exactly cubic? What are the symmetries? Rotation by 90 degrees through an axis passing through one of the faces of this cube. That is the symmetry I have over here. Let's say the gas or the liquid. If I have a liquid, if I rotate it in around any axis by any degree, it will stay the same. So liquids, and in fact gases, have the full rotational symmetry. But solid doesn't have the full rotational symmetry. So solids and liquids have more symmetry in that sense. But that change from full rotational symmetry to, let's say, the cubic symmetry, you cannot have it smoothly. It either exists, the cubic symmetry either exists or not. Full symmetry either exists or not. You cannot have half a symmetry. So that's what I mean by you can use this symmetry argument to distinguish a solid and a liquid or a gas. But there is no such argument for, let's say, liquid and a gas. If there's something that changes discretely, then in general you won't get these critical points. But if what you use to distinguish different phases, so-called phase parameters, if they can change continuously, like in the case of a liquid and gas, the phase parameter you use is usually the volume per molecule. Liquid have a small volume per molecule, gas has a huge volume per molecule. But this can, such a order parameter, let's say, if that is the only thing that distinguishes your phases, well, you do end up having these critical points. You can have smooth transition from one state to the other state. Well, let's calculate this one and then we can go for a break. What I would like to find is, let's say, what is the derivative of this pressure as a function of temperature? How does pressure change as a function of temperature along this coexistence line? So at least that will tell me whether the curves are increasing or decreasing as I change the temperature. Well, how can I do that? I know that along a coexistence line, the chemical potentials have to be equal. If I have two phases, A and B, the chemical potentials have to be equal. Why? Because, well, the same argument. If two phases exist together, along that line two phases will exist together. The chemical potentials of these two phases have to be equal. Well, the chemical potential I can write as a function of temperature and pressure. Now, if I restrict myself to changes along this coexistence line, pressure will be a function of temperature. You see, along these lines, you see, if you pick up, I don't know, this line, let's say, the liquid solid coexistence line. Along that line, pressure is given by the temperature. If you know the temperature, you know the pressure. So I have this equality. Well, what does this equality tell me? I can just take the derivative of both sides with respect to temperature, which will give me derivative of the chemical potential with respect to pressure times the derivative of pressure with respect to temperature, plus derivative of the chemical potential with respect to temperature. I'm just using the chain rule. The chemical potential has two arguments. Both arguments depend on the temperature. So if I want to take the derivative with respect to temperature, take the derivative with respect to the first argument times the derivative of the first argument with respect to temperature, plus the derivative of the second with respect to the second argument times the derivative of the second argument with respect to temperature, but that's just one. I can do the same thing on the other side. Now I can solve for the derivative of pressure with respect to temperature. Of course, in these derivatives of the chemical potential, I'm fixing the other parameter. So this is how the pressure changes as a function of temperature as I'm moving along the coexistence line. Well, it doesn't look so illuminating, but we will write it in a slightly different form in the next hour. So any questions before we go for a break? So basically what I have been doing, I just had a very simple model. I just looked at a gas and the oscillators. I first said that, okay, if the solid and the gas phases are in equilibrium, during a phase transition they will be equilibrium, their chemical potentials have to be equal, temperature has to be equal, so the fugacity, which is e to power beta mu, they have to be equal, which told me that the pressure during a phase transition depends only on the temperature. So basically, it doesn't depend on the volume. Then I constructed these diagrams. I know that at a very large volume, I would have a gas. The pressure will change as 1 over V. If I keep lowering the volume, eventually this equality eventually that equality will be satisfied, and then I have some solids in my system now. If I have solids in my system, the gas will still be there, the gas will solidify. Well, although I'm stating gas and solid, this will be valid in any phase transition. The gas and the solid are just easy to deal with our earlier simple model. We will have a mixture, and then if you lower the volume further, everything will solidify, and if you try to increase the volume, the pressure has to increase very fast. Solids are not so easy to compress. And then I looked at the question of what happens as we change the temperature though. Well, if we lower the temperature, if we start from a gas, we would expect it first to liquidify and then to solidify. This is what we are used to in our everyday life. But at a sufficiently low temperatures, sufficiently low pressures, let's say, it can solidify instantly without passing through this liquid phase. And if you are even at a higher pressure, very high pressure, you see over here. If your pressure is somewhere over here, there is no mixture. It doesn't mean that it has to happen. What I'm stating is, in general, not in general, you might have cases where you get a continuous change from one phase from what you call one phase to the other phase. So that is what happens above this critical point. Then I have all these boundaries in the PT plane, separating solids from gases, solid from liquid, liquid from gas. Then now I'm trying to understand, well, what determines the shape of these lines, these curves. Can I say something more about that? And well, I did obtain one relationship. I know how the pressure changes as a function of temperature in these coexistence curves, coexistence lines. Well, it doesn't look promising, but next hour we will just simplify it and express it in terms of other quantities that will be easy to understand. So let's give our 10-minute break and we will continue after the break.